Water heater. A water heater, usually fully automatic, has a storage tank with one or more electric heating elements and with operating and safety controls. Edwin Drood, a Norwegian mechanical engineer, was the inventor of the automatic storage water heater in 1889. A water heater consists of the following parts: a heavy inner steel tank that holds the hot water, insulation surrounding the tank, a dip tube to let cold water into the tank, a pipe to let hot water out of the tank, a thermostat to control the temperature of the water inside the tank, heating elements to heat the water, a drain valve that allows you to drain the tank to replace the elements or move the tank, a pressure relief valve, a sacrificial anode rod to help keep the steel tank from corroding. The cold water supply line connects to the water heater, typically on top of the appliance. Instead of dumping the water on top of the hot water in the tank, a dip tube carries the cold water down to the bottom of the tank. The outbound hot water line takes the water off the top of the tank. That way, when hot water is drawn out, it is at full temperature. Only after most of the hot water has been used do you start to get the hot and cold water mix. When you open a hot water tap, the water pressure from the cold water supply line pushes the water out of the water heater and refills the tank with cold water. As cold water enters the tank, the thermostat senses the lower temperature and triggers the heating mechanism. The thermostat controls the temperature of the water inside the tank. Normally, you can set the temperature between 120 and 180 degrees Fahrenheit. It is generally recommended that you keep the temperatures between 120 to 140 degrees Fahrenheit, especially if there are children living in the house, to prevent scalding. It also saves energy. Wind turbine. A wind turbine is a rotating machine which converts the kinetic energy in wind into mechanical energy. The first wind turbine was invented in 1888. The man who invented it was Charles F. Brush. When air moves quickly in the form of wind, those particles are moving quickly. Motion means kinetic energy which can be captured. The turbine blades are designed to capture the kinetic energy in wind. The rest is nearly identical to a hydroelectric setup. When the turbine blades capture wind energy and start moving, they spin a shaft that leads from the hub of the rotor to a generator. The generator turns that rotational energy into electricity. At its essence, generating electricity from the wind is all about transferring energy from one medium to another. The simplest possible wind energy turbine consists of three crucial parts: rotor blades, shaft, generator. There are two types of turbines: horizontal axis and vertical axis. VAWTs may be used for small-scale turbines and for pumping water in rural areas, but all commercially produced utility-scale wind turbines are horizontal axis wind turbines. The energy in the wind is converted to rotational motion by rotor. When the blade turns, the rotor turns a shaft which transfers the motion into the nacelle. The slowly rotating shaft enters a gearbox that greatly increases the rotational shaft speed. The output shaft is connected to a generator that converts the rotational movement into electricity at medium voltage. The electricity flows down heavy electric cables inside the tower to a transformer, which increases the voltage of the electric power to the distribution voltage. The distribution voltage power flows through the underground lines to collection point where the power may be combined with other turbines. The electricity may be sent to nearby farms, residents, and towns. The electricity may also be sent to a substation where the voltage is increased to transmission voltage power and sent through above-ground transmission lines to distant cities and factories. Escalator. An escalator is a power-driven, continuous moving stairway designed to transport passengers up and down short vertical distances. Escalators are one of the largest, most expensive machines people use on a regular basis, but they're also one of the simplest. Jesse W. Reno invented the first working escalator and installed it alongside the old iron pier at Coney Island, New York in 1896. The core of an escalator is a pair of chains looped around two pairs of gears. An electric motor turns the drive gears at the top, which rotate the chain loops. A typical escalator uses a 100 horsepower motor to rotate the gears. The motor and chain system are housed inside the truss, a metal structure extending between two floors. Instead of moving a flat surface as in a conveyor belt, the chain loops move a series of steps. The coolest thing about an escalator is the way these steps move. As the chains move, the steps always stay level. At the top and bottom of the escalator, the steps collapse on each other, creating a flat platform. This makes it easier to get on and off the escalator. In the diagram shown, you can see how the escalator does all of this. Each step in the escalator has two sets of wheels which roll along two separate tracks. The upper set are connected to the rotating chains and so are pulled by the drive gear at the top of the escalator. The other set of wheels simply glides along its track, following behind the first set. The tracks are spaced apart in such a way that each step will always remain level. At the top and bottom of the escalator, the tracks level off to a horizontal position, flattening the stairway. Each step has a series of grooves in it, so it will fit together with the steps behind it and in front of it during this flattening. In addition to rotating the main chain loops, the electric motor in an escalator also moves the handrails. A handrail is simply a rubber conveyor belt that is looped around a series of wheels. This belt is precisely configured so that it moves at exactly the same speed as the steps to give riders some stability. The escalator system isn't nearly as good as an elevator at lifting people dozens of stories, but it is much better at moving people a short distance. This is because of the escalator's high loading rate. Once an elevator is filled up, you have to wait for it to reach its floor and return before anybody else can get on. On an escalator, as soon as you load one person on, there's space for another. X-ray. X-rays are basically the same thing as visible light rays. Both are wave-like forms of electromagnetic energy carried by particles called photons. X-ray technology was invented completely by accident. In 1895, a German physicist named Wilhelm Röntgen made the discovery while experimenting with electron beams in a gas discharge tube. The X-ray machine is composed of an X-ray tube that contains a pair of electrodes or conductors called a cathode and an anode. The cathode is a filament that releases energy with the introduction of an electrical current, much like that of a light bulb. The cathode energy is released in the form of electrons. The anode, located on the opposite end of the X-ray tube, is a disc made of tungsten, a material that attracts the electrons. When the electrons released from the cathode come in contact with the tungsten, they release energy in the form of photons. These highly energized photons are channeled through a lead cylinder and a series of filters, creating an X-ray beam. The X-ray beam is a high-energy beam that can be absorbed only by dense body tissues such as bone. During an X-ray, a radiographic film is placed behind the patient and the patient is placed between the film and the X-ray machine. The X-ray machine then focuses the energy beam at the specific area of the patient's body. As the X-ray energy passes through the patient's body, the photons of the beam reach the film and cause a chemical reaction. The areas where X-ray energy passes through the body becomes black, while the areas where energy is absorbed by the bones appear white. This process produces a radiographic, which is commonly referred to as an X-ray. X-rays are not just used for imaging the human body for medical purposes. The same basic process is used to scan baggage at many airports, check suspicious packages at a post office or courier depot, and to scan the interior of walls to check for electrical lines and pipes before demolition of the wall. GPS. The Global Positioning System, or GPS, is a global navigation satellite system developed by the U.S. Department of Defense. It is a fleet of more than 24 communication satellites that transmit signals globally around the clock. With a GPS receiver, one can quickly and accurately determine the latitude, the longitude, and in most cases, the altitude of a point on or above the Earth's surface. Each of these 3,000 to 4,000 pound solar-powered satellites circles the globe at about 12,000 miles, making 2 complete rotations every day. The orbits are arranged so that at any time, anywhere on Earth, there are at least 4 satellites visible in the sky. Each satellite is constantly beaming out a radio wave signal towards the Earth. The receiver listens out for these signals, and if it can pick up signals from 3 or 4 different satellites, it can figure out your precise location. This operation is based on a simple mathematical principle called trilateration. Navigation involves measuring your distance from landmarks, but satellite navigation uses space satellites instead. Wherever you are on Earth, if you have a sat-nav receiver, it will pick up signals from orbiting navigation satellites. Although the satellites move, their exact positions are known. Each satellite beams the information out in all directions. Using signals from 3 different satellites, a receiver can pinpoint its own position. 1. Signal from satellite 1 tells receiver that its position must be somewhere on the green dotted line. 2. Signal from satellite 2 helps receiver to narrow its position to where blue and green dotted lines overlap. Signal from satellite 3 narrows down receiver's location to one point where all 3 dotted lines meet. Receiver uses signals from a minimum of 3 satellites to confirm exact position. Satellite navigation systems are incredibly accurate. Military versions of GPS receivers can pinpoint things to within just 5 centimeters. This incredible accuracy makes satellite navigation amazingly useful. It can show ships, aircraft, and cars where they are. It can help farmers to monitor their crop yield. And combined with an audio system that speaks out directions, it can even help blind people to navigate their way around unfamiliar places. Internet. The Internet is a global system of interconnected computer networks that interchange data by packet switching using the standardized Internet Protocol suite. It is a network of networks that consists of millions of private and public, academic, business, and government networks of local to global scope that are linked by copper wires, fiber optic cables, wireless connections, and other technologies. The father of Internet was Tim Berners-Lee. Besides Tim Berners-Lee, Vinton Cerf is also named as an Internet daddy. 10 years out of high school, Vinton Cerf began co-designing and co-developing the protocols and structure of what became the Internet. All of those developments took place between 1989 and 1991. One of the greatest things about the Internet is that nobody really owns it. It is a global collection of networks, both big and small. These networks connect together in many different ways to form the single entity that we know as the Internet. In fact, the very name comes from this idea of interconnected networks. Every computer that is connected to the Internet is part of a network, even the one in your home. For example, you may use a modem and dial a local number to connect to an Internet service provider. At work, you may be a part of a local area network, but you most likely still connect to the Internet using an ISP that your company has contracted with. When you connect to your ISP, you become part of their network. The ISP may then connect to a larger network and become part of their network. The Internet is simply a network of networks. Optical fiber. An optical fiber is a glass or plastic fiber that carries light along its length. They are arranged in bundles called optical cables and used to transmit light signals over long distances. Guiding of light by refraction, the principle that makes fiber optics possible, was first demonstrated by Daniel Colladon and Jacques Babinet in Paris in the early 1840s. If you look closely at a single optical fiber, you will see that it has the following parts. Core, thin glass center of the fiber where the light travels. Cladding, outer optical material surrounding the core that reflects the light back into the core. Buffer coating, plastic coating that protects the fiber from damage and moisture. Hundreds of thousands of these optical fibers are arranged in bundles in optical cables. The bundles are protected by the cable's outer covering called a jacket. Optical fibers come in 2 types, single model fibers and multi-model fibers. Fiber optic cables carry information between 2 places using entirely optical technology. Suppose you wanted to send information from your computer to a friend's house down the street using fiber optics. You could hook your computer up to a laser, which would convert electrical information from the computer into a series of light pulses. Then you'd fire the laser down the fiber optic cable. After traveling down the cable, the light beams would emerge at the other end. Your friend would need a photocell to turn the pulses of light back into electrical information his or her computer could understand. So the whole apparatus would be like a really neat high-tech version of the kind of telephone you can make out of 2 baked bean cans and a length of string. Optical fibers carry light signals down them in modes. A mode is the path that a light beam follows down the fiber. One mode is simply to go straight down the middle of the fiber. Another is to bounce down the fiber at a shallow angle. Other modes involve bouncing down the fiber at other angles more or less steep. Optical fibers are widely used in fiber optic communications, which permits transmission over longer distances and at higher bandwidths than other forms of communications. Satellite TV. Satellite television is television derived by the means of communications satellite and received by a satellite dish and set-top box. Both broadcast television and satellite stations transmit programming via a radio signal. Conceptually, satellite television is a lot like broadcast television. It's a wireless system for delivering television programming directly to a viewer's house. The first satellite television signal was relayed from Europe to the Telstar satellite over North America in 1962. Satellite television systems transmit and receive radio signals using specialized antennas called satellite dishes. The television satellites are all in geosynchronous orbit, meaning that they stay in one place in the sky relative to the Earth. Each satellite is launched into space at about 7,000 mph, reaching approximately 22,200 miles above the Earth. At this speed and altitude, the satellite will revolve around the planet once every 24 hours, the same period of time it takes the Earth to make one full rotation. In other words, the satellite keeps pace with our moving planet exactly. This way, you will only have to direct the dish at the satellite once, and from then on it picks up the signal without adjustment, at least when everything works right. There are 5 major components involved in a DTH, or direct-to-home satellite system: the programming source, the broadcast center, the satellite dish, and the receiver. Programming sources are simply the channels that provide programming for broadcast. The provider doesn't create original programming itself. It pays other companies, for example, HBO or ESPN, for the right to broadcast their content via satellite. In this way, the provider is kind of like a broker between you and the actual programming sources. The broadcast center is the central hub of the system. At the broadcast center, the television provider receives signals from various programming sources and beams a broadcast signal to satellites in geostationary orbit. The satellites receive the signals from the broadcast station and rebroadcast them to the ground. The viewer's dish picks up the signal from the satellite and passes it on to the receiver in the viewer's house. The receiver processes the signal and passes it on to a standard television. Receivers have a number of other features as well. They pick up a programming schedule signal from the provider and present this information in an on-screen programming guide. Lock. There are many different kinds of lock and they often work in very different ways, but one of the most common is the cylinder pin tumbler lock used in padlocks and Yale door locks. Based on a mechanism invented in ancient Egypt, it becomes a winning invention in the 1860s thanks to the efforts of American inventor Linus Yale Jr. and the Yale Company named for him. The heart of a lock is a sturdy metal cylinder that can swivel inside an equally sturdy metal housing. When the key is in place, you can turn the cylinder freely and open the lock. Without the key, the cylinder refuses to turn and the lock stays shut. Inside a cylinder lock, there is a sort of puzzle which only the correct key can solve. The main components in the pin and tumbler design are a series of small pins of varying length. The pins are divided up into pairs. Each pair rests in a shaft running through the central cylinder plug and into the housing around the plug. Springs at the top of the shafts keep the pin pairs in position in the plug. When no key is inserted, the bottom pin in each pair is completely inside the plug, while the upper pin is halfway in the plug and halfway in the housing. The position of these series of notches in the key push the pin pairs up to different levels. The incorrect key will push the pins so that most of the top pins are still partly in the plug and partly in the housing, prevents the cylinder from turning. The correct key will push each pin pair up just enough so that the point where the two pins come together lines up perfectly with the space where the cylinder and the housing come together. To put it another way, the key will push the pins up so that all of the upper pins are inserted completely in the housing, while all of the lower pins rest completely in the plug. Without any pins binding it to the housing, the plug moves freely and you can push the bolt in and out. Refrigerator. A refrigerator is a cooling appliance comprising a thermally insulated compartment and a heat pump, a mechanism to transfer heat from it to the external environment, cooling the contents to a temperature below ambient. The first known artificial refrigeration was demonstrated by William Cullen at the University of Glasgow in 1748. A refrigerator does not cool items by lowering their original temperature. Instead, an evaporating gas called a refrigerant draws heat away, leaving the surrounding area much colder. The refrigeration process begins with the compressor. Ammonia gas is compressed until it becomes very hot from the increased pressure. This heated gas flows through the coils behind the refrigerator, which allow excess heat to be released into the surrounding air. This is why users sometimes feel warm air circulating around the fridge. Eventually, the ammonia cools down to the point where it becomes a liquid. This liquid form of ammonia is then forced through a device called an expansion valve. Essentially, the expansion valve has such a small opening that the liquid ammonia is turned into a very cold, fast-moving mist, evaporating as it travels through the coils in the freezer. Since this evaporation occurs at -27 degrees Fahrenheit, the ammonia draws heat from the surrounding area. The coils inside the refrigerator allow the refrigerant to absorb heat, making the inside of the refrigerator cold. The cycle then repeats. The ammonia gas is drawn back into the compressor, where the entire cycle of pressurization, cooling, and evaporation begins anew. Flush toilet. A flush toilet is a toilet that disposes of human waste by using water to flush it through a drain pipe to another location. Flush toilets were first used in the Indus Valley civilization. The cities of Harappa and Mohenjo-daro had a flush toilet in almost every house, attached to a sophisticated sewage system. In 1775, Alexander Cummings invented the S-trap, which is still used today. That used standing water to seal the outlet of the bowl, preventing the escape of foul air from the sewer. Later, plumbers Joseph Brummer and Thomas Twyford further developed the technology with improvement such as the float and valve system. The picture below shows a typical toilet. The toilet bowl usually has a ring-shaped seat on a top, which is covered by the lid when not in use. The handle or sometimes a button is pressed to flush the toilet. The water used for flushing is stored in the tank. The tank contains some important parts. The inlet valve controls the water supply coming into the tank. It lets water in when the tank is empty and stops water coming in when the tank is full. The float ball rises as the tank fills with water. As it rises, the float rod attached to it presses against the inlet valve. When the tank is full, the rod is pressing against the inlet valve hard enough to turn the water off. This stops the tank from overflowing. When you press the handle, a lever inside the tank pulls the piston up, forcing some water through the siphon. This provides suction in the siphon, and the rest of the water follows, emptying the tank. The tank empties quite quickly, and the float ball floats to the bottom. That means the float rod is no longer pressing against the valve, so water begins to flow into the tank, filling it up again. The water which left the tank goes through a short pipe to the toilet bowl. It sloshes around the rim, down the sides of the bowl, and out through the drain pipe, cleaning the bowl and carrying the waste with it. Some of the clean water coming behind remains at the bottom of the toilet bowl. That's because the modern toilets have an S-bend which remains filled with water between flushing. The water in the S-bend stops bad odors escaping from the drain pipe. During flushing, the S-bend also provides siphon action which helps speed up the flushing process. Light bulb. Before the invention of the light bulb, illuminating the world after the sun went down was a messy, arduous, hazardous task. It took a bunch of candles or torches to fully light up a good-sized room, and oil lamps, while fairly effective, tended to leave a residue of soot on anything in their general vicinity. Englishman Sir Joseph Swan and American Thomas Edison both got it right around the same time, and within 25 years, millions of people around the world had installed electrical lighting in their homes. Light bulbs have a very simple structure. At the base, they have two metal contacts which connect to the ends of an electrical circuit. The metal contacts are attached to two stiff wires which are attached to a thin metal filament. The filament sits in the middle of the bulb, held up by a glass mount. The wires and the filament are housed in a glass bulb which is filled with an inert gas such as argon. When the bulb is hooked up to a power supply, an electric current flows from one contact to the other through the wires and the tungsten filament. The tungsten is very thin and coiled to maximize resistance in the wire. When electricity meets resistance, it heats up the resistor. The tungsten gets to a temperature of about 4,500 degrees Fahrenheit. This causes it to get white hot. It glows and glows quite brightly. Tungsten is used because it has very high melting point. The tungsten is encased in a bulb for good reason. Not only does it protect people and objects from the hot tungsten, it also keeps oxygen away from the hot metal, which would make it immediately burn up. The bulb is usually filled with a low-pressure, inert gas such as argon.